All right, we're moving into global weather now. Think of global weather as if you just kind of looked at the whole globe and wanted to look at the big picture. You're not looking at details. You're not looking at little individual station areas or small things. You're looking at, oh, there's low pressure. It's a big area. There's a high pressure. It's a big area. So that's what we're going to talk about this week. So the reason these features are where they are on the globe is because of the Earth's rotation, the sun, the humidity of the oceans. All of these factors that you've learned about a little bit now play into why we have this pattern. So here's a current surface analysis. Nothing fancy. Notice there are low pressures up here around 50 to 60 degrees north. Several of them, as a matter of fact. 1, 2, 3 at least. Now you go south, and you get some lows coming through. But I want you to go down further south here if we can. There you go. And what we eventually find a lot of is there's more high pressure further south, and especially around 30 degrees. You ever hear of the Bermuda? It's high pressure that's right off the coast, southeast United States. It kind of sits there, and it becomes a little stronger in the summer, a little weaker in the winter, and it influences a lot of the east coast of the United States. There's another high pressure, 30 degrees off the coast of California, at about the same latitude. Now, what have you learned about the flow around high pressures? High pressures have clockwise flow of wind, right, and air. So if you're on the east coast of the United States, the air coming off of that high is coming in from the Atlantic Ocean, southeast Atlantic, and into the southern part of the United States. Well, southeast Atlantic is warm, it's humid. Now, California, the air is coming in from the northwest. Well, what's up there? Cooler ocean temperatures. Yeah, there's moisture, but it's much, much cooler. So why does California not get as hot and humid as southeastern United States? It's because the air is coming in from the north more. So it winds up being less humid a little bit, and definitely not nearly as warm. So that's an overview, just to think about it, of the general climate of the Earth. And if you flipped it in the southern hemisphere, you'd find the same thing. So with that in mind, another aspect of global climate is things, large-scale weather patterns like La Nina or El Nino. They're not actually weather patterns. They're a combination of the ocean and weather. So the two combined. What is an El Nino or a La Nina or an ENSO? All three are the same. ENSO is basically the broad category. El Nino. It means that temperatures anomalies along the Pacific near the equator, a little above it, are generally running above normal average. So here is this temperature anomaly. This was in the winter, back in January or so. Notice it was almost close to 2 degrees Celsius above normal. Now, at the same time, we come to the present. And notice we take Nino lesion 3.4 as kind of where we look for El Nino or La Nina. It has come down to pretty much normal here with the averages. And it's projected to go down into the other range below normal. So, and if an El Nino is temperatures above normal, significantly, we got to have at least half a degree to a degree above normal over 3-month average, which we obviously had here in the winter. La Nina is just the same, except it's going to be at least minus a half a degree or more, averaged over 3 months. So we don't have that yet, but that is the trend of where we're going. This is a pattern influenced by the ocean currents and the winds. The two work together to change the temperatures of the Pacific Ocean. And these temperature changes then influence a lot of how the global winds flow. During El Nino, for example, there's more air being pushed up. Obviously, the ocean's warmer out there, so you wind up changing the influence and the wind flow pattern. It may actually stop the normal easterly winds in the tropics that we have and create stronger westerlies in the wintertime. Now, when we go to La Nina, well, we don't have as much air going up into the sky. That's moisture, maybe in the Pacific. So you wound up allowing a stronger trade wind or a stronger easterly flow in the tropics. That's why there's less shear when you have the hurricanes. And also, it weakens the winds, the jet streams in the north, so they become more pronounced and typically allow colder air to get in the United States. Another global feature is monsoons, and we actually have one in the United States. So what I wanted to show you is I'm looking at a map of Tucson, Arizona. Tucson is extremely influenced by monsoonal flow. What happens? Well, you have high mountains in Mexico that heat up in the summertime. They're not getting anything but a lot of solar radiation into them. They get very hot. They allow a low pressure system to form at the surface. And remember, when it's very hot, the pressure doesn't change as much in the vertical. So they're going up in a slower rate of pressure change. So you actually wind up with high pressure aloft. So this is a very stable pattern. When it sets in, think about it, have low pressure at the surface, high pressure divergence aloft. What happens is you wind up pulling moisture in from the Gulf of Mexico and the southeastern Pacific into the area where the low pressure is, which then flows up into places like Arizona, southern parts of California, New Mexico, that area. Yes, it's not going to be strong all the time, but it lasts a lot of the summer season. And when you're looking down here, one of the things that's really interesting, look at the rainfall. All of a sudden, the rainfall went up starting in late June, and it just kind of keeps going up above normal. This is the time of year when places like Tucson and all get a lot of their rain. Lightning strikes go up at this time. And look at the dew point tracker. Dew points in the 20s, in the low 30s here. All of a sudden, now they've been sitting in the 60s and 50s, which is, for out west, fairly high dew points. So I wanted you to notice all of this as we go about what we're going to talk about today. So these are current things going on. So now we're going to look at the atmosphere's planetary circulation. So with that in mind, we come up with a reasoning behind some of that planetary circulation. So what are some of the features that govern it? Well, let's go back here a minute. Now, I'll go through it here a minute. Part of the features are the Earth's rotation and the way the temperatures change. And they change because of solar radiation. So we wind up with three belts. High pressure along 30 degrees north because winds are kind of rotating towards the equator. Divergence at around 30 degrees north. Convergence a little further up near 60 degrees north. So we have these main belts of winds. And across us, you'll notice the winds are out of the southwest or west or westerlies. So if we didn't have a rotating planet and if we had the sun directly on the same spot, what you would have is one side of the Earth would be heating up and the other side would be getting very cold. You would basically have air flowing up from the hot air around the globe, coming down where it's coldest. And then repeat the cycle. But we don't have that. We have a rotation and we have that. So this changes where we have high pressures and low pressures. Here is a semi-permanent pattern. The intertropical convergence zone. That is where, basically along the equator, close to where the hottest air is. So it's going to move north with the sun in the wintertime and south with the sun in the summertime. And as it moves, you can see in January here we have low pressures along the north. Mid-latitudes, we have the high pressure. Further south, the intertropical convergence zone, actually south of the equator. And summertime, the intertropical convergence zone moves back north. Interestingly, the intertropical convergence moves north further over land than it does over water. Why is that? Well, water takes a whole lot more heat to warm up, doesn't it? We learned that latent heat of water, specific heat of water, is a lot higher than the land mass. So with that in mind, the oceans may warm, but they won't warm as fast as land. So that the land heats up even more. So therefore, where the lowest pressure is in intertropical convergence zone in the summertime is always going to be further north in our summertime. So that changes the flow pattern across a lot of places over land. So on the eastern sides of high pressure systems that are around 30 degrees north, we have sinking, a lot of fair skies, and that's basically where the deserts. Guess where the deserts are in the United States? Southwestern United States, eastern part of the flank of this high. We have the lows that move across well to the north, and we have fronts riding across between them. We have our polar vortex way up north as well. Influences a lot of how much Arctic air can get into our area. And we have our westerlies, kind of a wavy pattern to them. Tropopauses. Think about it. Up close to the poles, always cold. Tropopause is fairly low because we know pressure changes very quickly in cold air. However, down over the tropics, in the same token, it's fairly warm. Between that tropopause will fluctuate a lot. Along the trade winds, we can see the different branches of how flow works and how the intertropical convergence zone, here it really shows it to you. Look how much further north it is in July than it is in January, over land. While over the ocean, you see it hardly moves at all, the same over here. Because of that, it creates what we call monsoons. We've talked about one out in the United States. Here's another one that actually occurs in Southeast Asia, India. In the summertime, the intertropical convergence zone moves north with the land. It actually moves into northern India, parts of China. And what's it do? It changes the flow of wind so that they come off the water to the south. Lots of moisture. Now, in the wintertime, that intertropical convergence zone flows back south, goes back over the water. What do you get? Well, you got north of you a very dry continent, right? Siberia is up there. So they wind up not getting as much moisture or rain. So you can see these large highs have a major influence on the amount of precipitation we get. They also influence the ocean currents. The Gulf Stream in the United States that flows out from the Gulf of Mexico and up along the East Coast is influenced by that high pressure system. And here is our general pattern for the southwest monsoon we talked about earlier. Okay, Rossby waves are very big, long waves in the atmosphere. What we call long waves. A wavelength are long. So if the wavelength is long, maybe covering much of the United States or the eastern two-thirds of the United States, might be a Rossby wave. When you look far to the northern part, basically above 40 or 50 degrees north, you can kind of pick these patterns out where a long wave is there. And then inside that long wave are a number of little tiny waves, shorter waves. As they rotate through the long waves, they intensify where the Rossby waves are the strongest and the steepest down, and they'll get weaker when they go through where the ridges of high pressure are. So as these Rossby waves move around the world, and they do move, it changes our weather here as to whether we have stronger lows, maybe more high pressure. And with that in mind, you get what we call zonal and meridional flows. Meridional flows are strong, upper level, southerly flow, well to pull a lot of very cold air out of Canada if it's over the United States. At the same time, it's going to pull a lot of very warm air out of the Gulf of Mexico, maybe even the Caribbean Ocean, Caribbean Sea, in the United States. It's a temperature contrast. So I am really nice and warm today. Oh wow, it is bitter cold the next day. That is on a marine level. Those do have temperature contrast, but not as strong. So they may, and they'll move much faster, where meridional flows may move slowly across the globe. Zonal flows move very quickly. And we can also wind up with blocks, sometimes, especially in the spring and the fall. We get patterns that get blocked where you just get if you were to look at a stream and a river, sometimes you see rocks or whatever where you just keep going in circles. The flow of water around that rock. Well, the same kind of thing kind of happens in the atmosphere. And when they get blocked, you wind up getting record rainfalls or record snowfalls, many records temperatures. When you go aloft, all right, we've talked about many times how the air density changes with temperature. Well, all right, so if I'm doing that, where is the most change going to be in air pressure? The higher up, because you've had more and more time for over the warm air, the pressure not to drop as fast, and over the cold air, the pressure to drop faster. So you wind up with the greatest pressure change very high up in the troposphere, really close to the tropopause. Where that strong pressure, horizontal pressure gradient is, we know that's where the winds are going to be strongest. That's where your jet streams occur. And it's all because of this contrast between the warm and the cold air masses. So where does that contrast be the greatest? Along a front, right? So if you have the stronger the front, the stronger the jet stream is going to likely be. And we know the Coriolis effect works on this as well. And so the summer jet stream in the United States, typically up in the north, across the Great Lakes. Winter jet stream comes down closer in the southern part of the United States. I talked about the Rossby waves, and I've talked about little short waves rippling through them. We're going to get into a whole lot more of that when we talk about mid-latitude weather. In order to form an extratropical cyclone, we need to have divergence aloft. So on the front side of a wave, low pressure, where the trough occurs, is going to be divergence, typically along the jet. With that divergence, then at the surface, we're going to wind up with air wanting to rise. If air is rising, it's causing low pressure. So that's where your low pressure will form. And here you can see the jet streaks. They're basically areas of really fast wind. And there will be different ones that are around the globe at all times. They're changing constantly. They're moving through the flow. And depending on where you are in relation to that jet streak is where you're going to have divergence or convergence aloft, which makes a major influence on what your weather is at the surface. We've talked about El Nino and La Nina and how they move. Ekman's spiral. I think of this one along the East Coast. I live in Virginia Beach area, but I have been to the Outer Banks, and I have a lot of friends that go to the Outer Banks, like to surf, like to swim, and they've experienced the Ekman spiral in a dramatic fashion. Along the east coast of the United States in the summertime, winds are coming around that big Bermuda high situated out there. We have a lot of southerly winds. So what's that going to do to the water? The water is going to move to the north, right? Well, if the water is moving to the north, Coriolis effect is going to push it out to sea, right? So as it's doing that, sometimes it moves it out more some days than others. The velocity is more. And when it turns it more, well, where's that water going to come from that's going to replace that ocean water that's turned away from the coast? It's coming from the deep ocean. So it's bringing up water from the deep where it's much cooler, and you can get dramatic temperature changes. Sometimes off of Cape Hatteras, the temperature can drop 30 to 40 degrees on the water in one day. And we talked about El Nino and La Nina a little bit. All right, there's another circulation called the North Atlantic Oscillation. When you look at a global thing, you know there's going to be a low pressure up to the north, high pressure to the south. How dramatic that pressure gradient is has a major impact. We've learned on the east coast of the eastern half of the United States, really, and over in Europe. So depending on how that plays out, we may have a lot more cold air, a lot more snow, or a lot more warm air and milder weather. That is a major influence, especially in the wintertime. So we always monitor that to see how it's going. So basically, the positive phase is saying you have a much stronger low, much more powerful over the north, and you can see it changes. Colder winters north of the polar front, warmer winters south. And here's the rainfall pattern, negative index, just a different pattern. So, Arctic oscillation. All right, we talked about there being a very strong upper level low in the Arctics all winter long and all summer long. Not as strong in the summer. Think about it. If that low is very strong, the winds are going to be circulating very fast around it, right? Well, that doesn't allow that really Arctic air to get out and come into the United States. Now, if that Arctic oscillation is a little weaker, it allows more of the cold air to get in the United States. Look at that to determine, well, if it's shifting, what the forecast is says, oh, it's going to be shifting to a more weaker, maybe even negative pattern. We're going to expect more Arctic air to come in the United States. If it's stronger, we can expect less. And then there's Pacific decadal oscillation as well, which influences more the Pacific coast. All right, Madden-Julian oscillation. There's an area of thunderstorms that typically seem to form over the Indian Ocean and literally produce a circulation in the atmosphere that flows around the globe. Doesn't move fast, but it takes about 30 to 60 days to go around the globe. It impacts rainfall. It impacts clear weather. It has major impacts as it's moving around the globe. It can enhance tropical weather or it can kill it. So depending on which side of the MJO we're on. So it's something that we've just learned about back in about the last 20 years or so. So we've been doing more studies on it and looking at it. It has a major impact on atmospheric rivers coming into the west coast of the United States. If you're in a enhanced precipitation part of the circulation, it's going to bring more rain to California. So I hope you got a little bit out. If you have any questions, please don't hesitate to ask.